So, hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So, we will be going over some of the concepts that we learned in the last 3 weeks. Stability, as I've mentioned in the previous two lectures, is the initial tendency of a system, of a plant to go back to its original state. Okay, so if it's subject to a disturbance, the tendency to go back to its equilibrium is called static stability. Dynamic stability would deal with its tendency to go back to equilibrium over a period of time. So static stability is just the initial tendency to go back to its equilibrium. The point about which we do all the analysis for an aircraft or a wing is the aerodynamic center. It's all of the forces, like I said before, they act about a point called center of pressure, but this varies with flight. So we have chosen a point called aerodynamic center, about which the pitching moment is constant with angle of attack, is independent of angle of attack. It remains constant throughout the flight. So this point is used for all of your analysis. So when we transfer the forces acting at the center of pressure to the aerodynamic center, it comes with a moment. That is the pitching moment at the aerodynamic center, CMAC. The pitching moment equation is given here. Cm is Cm naught plus dCm by d alpha into alpha. And the condition for static stability for an aircraft to be longitudinally statically stable is this dCm by d alpha. Cm alpha should be less than 0. That means the slope of that line should be negative. And so that is the graph that we know very well by now. So the Cm versus alpha graph would be negative. Now, this is Cm naught. In order to trim the aircraft at a positive angle of attack, we need Cm naught to be positive. We had discussed the two ways in which we can make Cm naught positive in the last lecture. One of them is to have a negative tail setting angle. And the other way is to have a reflex airfoil, which will give you a positive Cm naught, which will give you positive CMAC at the wing. This is because for the reflex airfoil, the forces give a positive moment at the aerodynamic center. Positive is pitch up. So the two contributions of the wing and tail towards the pitching moment at the CG are given here. The first terms of both these equations contribute towards Cm naught, which is why I said this tail setting angle contributes towards positive Cm naught, and this value contributes towards Cm naught. The other two terms, these ones represent the slope of the graph, dCm by d alpha, Cm alpha, which are an indication of the stability. So Cm alpha negative corresponds to statically stable aircraft. Then we studied neutral point. Neutral point of an aircraft is analogous to the neutral point to the aerodynamic center of a wing. It is the point about which the pitching moment is independent of angle of attack. Neutral point is for an aircraft, and aerodynamic center is for a wing. So a neutral point is the CG location at which Cm alpha is 0. That is, the slope is 0. So the equation for neutral point is given here. Next, we study static margin. Static margin is a measure of the stability of the aircraft. So larger the static margin, larger the distance between the neutral point and the CG of the aircraft, larger is the stability. So greater static margin corresponds to more stable aircraft. It also is represented by dCm by dCl, minus dCm by dCl. So your dCm by CL graph is this. It is the negative slope. So your static margin would be, for a stable aircraft, would be positive. This is Cm and this is Cl. So the negative slope of this graph is the static margin. It represents the distance between the neutral point and the CG of the aircraft. These are a few of the formulas that we use during the numericals. So the first two, that is this epsilon naught and the slope of epsilon with alpha, they tell you about the downwash. Downwash is the change in angle of attack that is seen at the tail due to the effects of the wing. So when the angle of attack seen at the wing and the tail are different, there is a reduction in the angle of attack at the tail due to the after effects of the flow over the wing. So these two terms, so the equation would be epsilon is equal to epsilon naught plus epsilon by d alpha into alpha. So these two terms give you the variation of this downwash angle. Then is VH. VH is the horizontal tail volume ratio. So this is the term that comes in the tail contribution stability part. Let's do this. this VH is the vertical tail, horizontal tail volume ratio. Ma'am, how do we know if CL alpha is 3D or 2D and when to convert to one another? So if it's given that the CL alpha is for the wing, it's 3D. If it's for the airfoil, it is 2D. Is that clear? Is that clear, Devansh? Okay. And usually for this CL alpha 2D, it's represented by small alphabets, and for 3D, it's capital letters. So this is the equation that he was referring to. This is how we convert the. So here you can see that CL is small for 2D and L is capital for 3D. It's usually represented this way. This is the equation that enables us to convert the slope, the lift curve slope from 2D, that is for an airfoil, to 3D, that is for a wing. So this is how we convert from 2D to 3D. Then we moved on to control, the longitudinal control of an aircraft. Why do we need control? So we have why we convert. Okay, so we have studied the CL alpha. I think in the previous aircraft performance class, we have studied CL alpha. This lift curve slope, CL versus alpha, is given for a 2D airfoil. But when we do the analysis for an aircraft, we have a wing. It's no longer an airfoil, but it's a wing of finite length. So due to the effects of the flow over a 3D object, it will not be, the lift curve slope will not be the same as for an airfoil. Okay, so when the air flows over the wing, over the finite length wing above and below, one of the effects is that at the tip, at wing tip, you have vortices. So this flow, so there's a wing here. At the tip, you have a flow coming from down and you have a flow coming from above. So at the point where it interacts, there are vortices generated. So that was the reason we have wing tips. We had discussed this, I think, in the first tutorial. So this is one of the effects that are not seen in an airfoil, in a 2D airfoil, but are seen in a wing. So due to these effects, we need to convert the lift curve slope of a 2D airfoil into 3D wing. Is it clear now? Is it clear? So we were discussing why we need to incorporate control. So for a given aircraft, the value of trim, CM versus CL. So this is the CM-CL graph, okay? So at trim means sum of all forces, sum of all moments is 0. So in this case, this point is trim. So this is the amount, this is the CL trim. Now say we want to trim the aircraft at a different CL, that is at a different velocity. At a lesser velocity means higher CL. So now this is the CL new trim. We wish to trim the aircraft at this new CL. So this control surfaces in our case for longitudinal control is the elevator. Elevator is the control surface that is present on the horizontal tail, and that is used to control the longitudinal motion. So that control surface helps us to trim the aircraft at the new velocity or the new CL. So what it does is it translates the graph. So it moves the graph. It doesn't do anything to the slope. It changes the intercept. So I'll just draw this clearly. Original line was like this. New line is like this. So CM0 2 and CM0 1. So the control surface effectively changes the intercept. It doesn't change the slope. So it has no effect on the stability. Remember that the stability was the slope, dCm by dCl. That represented the static margin, right? So static margin was minus dCm by dCl. That was the measure for longitudinal stability. So this control surface has no effect on stability. It just changes the value of CL at which we want to trim the aircraft. Okay, so it doesn't change the slope. It has no effect on dCm by dCl or CM alpha. It just changes the CM0, the intercept. Now some conventions, elevator down is considered positive. Why is it considered positive? So suppose this is the CG of an aircraft and this is your tail and this is your elevator. So if it's elevator down, as opposed to the original configuration, this has more lift. So delta L would be greater, right? Change in lift when you deflect the elevator down would be positive, would be a greater value. So this extra lift contributes towards a nose down moment, which contributes towards stability, right? So when it's subjected to a positive angle of attack disturbance, when you give a pitch down motion, it is contributing towards stability. So elevator down contributes towards pitch down, and that is considered positive. So elevator down, which generates a nose down moment, is the positive convention. We can describe this as the zero lift line changes. So suppose you have, sorry, just erase that. Okay. So you have an elevator, suppose say it's zero angle of attack. This produces no lift. But if we deflect the elevator down, sorry, this, if you have a tail at zero angle of attack, so the alpha, this is alpha equal to 0. But if we deflect the elevator down, even at zero angle of attack, you have some lift. So having a control surface is analogous to changing the zero lift line. So your CL versus alpha, this is the original CL versus alpha, the symmetric airfoil. But when you deflect the elevator, okay, sorry. How will the CL versus alpha graph look for a symmetric airfoil? Can anybody tell me what would be the slope and the intercept? Positive slope, negative slope, intercept, what would the values be? For us?
Positive and intersect with origin.
Sorry, can you say that again?
Slope is positive and intersect is start from origin.
Okay, correct. For a symmetric airfoil, so for a symmetric airfoil, you would have, it would look like this, CL and alpha. But if we deflect the elevator, we have lift produced even at zero angle of attack. So what happens is you have this, correct, positive intercept at 0. Okay, so you have a lift generated even at a zero angle of attack. Okay, is that clear?
Yes, ma'am.
Okay. So we can interpret the elevator down or elevator control surfaces as a change in the zero lift line. Another thing that we have, so this line corresponds to symmetric airfoil, right? Symmetric. And this line corresponds to a cambered airfoil, because for a cambered airfoil, we have positive lift at zero angle of attack. So we can interpret the control surface either as a change in the zero lift line or as a change in camber. From symmetric to cambered airfoil we are going. Okay, so these are the two interpretations, physical interpretations of your deflection of elevator, deflection of control surfaces in general. Next, we have the two equations, CL delta E and CM delta E. That is the variation of lift with change in elevator deflection. So this is a positive quantity because your areas are positive. The efficiency factor, tail efficiency factor is positive. CL alpha T is positive. You have a positive slope, lift curve slope. And tau, which is the control surface effectiveness parameter, represented by D alpha T by D delta E, is positive. So this entire term, CL delta E, is positive. CM delta E is given by this equation. And again, all of the individual parameters are positive, but it has a negative sign. So CM delta E is always negative. Next, we have the equation for delta E trim for a given CL trim. So if I were to draw the graph here, delta E and CL, how would the graph look? So first, let's concentrate on the slope. This is the value for slope. This value is positive or negative. So XNP minus XCG is the static margin. Static margin for a stable aircraft, is it positive or negative? Is it positive or negative?
Positive.
Positive, yeah. So this is positive. And the CM delta E is what? CM delta E we just discussed. CM delta E, this value is negative. So the overall slope, that is this entire term, would be negative. Okay, so the slope would be negative and intercept. Now CM naught is positive or negative? For if we assume that the aircraft is trimmed at a positive angle of attack, CM naught is positive or negative?
Positive.
Positive. So Cm naught is positive. Cm delta E again negative. So this entire term would be positive. So you have a positive delta E naught. So this would be the slope. Correct? You agree with me?
Yes.
So this equation would be delta E naught plus d delta E by dCl at trim and Cl trim. So this slope is negative and this is positive. So the graph would look like this, right? Okay. So now let's see what happens if the CG moves close to NP. So now our graph is like this. This is delta E and this is Cl. So if, for example, if your CG is at neutral point, how would the graph look? Slope would be 0, right? So the graph would be like this. So as the CG moves closer to your neutral point, this is CG2, CG1, to CG1. So as your CG moves closer to the neutral point, the slope keeps reducing until it becomes 0. So if your aircraft is flying, if your aircraft has CG at the neutral point, the d delta E by dCl would have a constant, would have 0 slope. So it would not change with Cl. Okay. This is the interpretation of that equation. Now, so some questions that were asked in the forum: is CMCG about wing CG or aircraft CG? CMCG we calculate about the CG of the wing, CG of the aircraft. So the analysis that was done. So we had a wing here, and we had a tail here, and what we did is we calculated the effect of these forces about the CG of the aircraft. CG of the aircraft. I think it was wrongly written in one of the slides, but it's always, the moment is always about MCG. Okay, the forces are calculated, the moment of the forces are calculated about the CG of the aircraft. Okay. Next was, how does Cm alpha equal to 0 mean that the aircraft is statically stable? What is static stability? So if your aircraft is flying at equilibrium and it is suddenly subject to a disturbance and the alpha changes. So this was the equilibrium position of the wing. Suddenly it's subject to a disturbance and the alpha changes. So static stability is the, okay, let's see, this is alpha. Initially alpha was 0. This is some positive alpha. So static stability was described as the initial tendency of the aircraft to go back to its equilibrium. Now, since this is nose up, so you have a pitch up, nose up motion. For the aircraft, for the wing to be statically stable, what moment should you have? What moment should this wing have for it to be statically stable? It was subject to a positive moment change for pitch up. So what moment should it have for it to be stable, statically stable? Cm should be positive moment or negative moment? Pitch up or pitch down? Can somebody tell me? Nose down, yes. So it should have a pitch down motion, which is why our slope was negative, right? Cm alpha. So with a change, positive change in alpha, you need to have a negative pitching moment to negate the effect of the disturbance. Okay, so you need to have a negative Cm for a positive disturbance. So that is why your slope was negative. Now, if your slope was 0, with any change in alpha, your Cm remains constant, right? So even if the aircraft changes to a larger alpha, it will have no restoring moment. Your Cm is remaining constant. No matter what the alpha is, your Cm is remaining constant. So it will have no restoring moment. It will have no initial tendency to go back to equilibrium. So the aircraft is not statically stable. It remains at that position. There is no change in the moment. So it is neutrally stable. Neutrally stable is what? Stable at the new location. So is that clear? The second point, the second question, why Cm alpha means that the aircraft is, neutrally stable. There's a mistake here. Why Cm alpha means that the aircraft is neutrally stable. That was the question. Okay. Let's correct this. Is that clear now? I'm not sure who asked the question, but is that concept clear? Can somebody confirm? It's clear. Next question was, how did we get dCm by d alpha as Cm alpha? I'm not sure if I made this clear, but that is just the notation. So Cm alpha, so Cm alpha is nothing but dCm by d alpha, right? So that is just a term notation that we use to ease our writing. Can you please repeat the neutral part? Okay, so let me clear the screen. So your aircraft was initially, your wing, let's take wing, okay? Wing was initially at equilibrium, say at angle of attack 2, alpha equal to 2. So this is your equilibrium point, okay? So now it is subject to a gust and the angle of attack changes to 4. Angle of attack is now 4, but your equilibrium was at alpha equal to 2. So now there is a disturbance that made your wing pitch up. So now for the aircraft, for the wing to be stable, you need to return to equilibrium point. You need to have the tendency to return to equilibrium point. So that what do you need? This pitched up to go to this position, right? Now you need to have a restoring moment. To counter this pitch up moment, you need to have a restoring moment. That should be pitched down. So you should have, when the wing is subject to a positive pitching motion, you should have a restoring negative moment. This restoring moment. You should have a negative restoring moment, which is why your Cm alpha, Cm versus alpha, graph was negative. For a change, for a positive change in alpha, you need to have a negative pitching moment. Okay? Is it clear now? Is this part clear? Who asked the question? Jay, is that clear? Okay. Now, if your graph, if your Cm versus alpha graph had a zero slope, 1 second. So if your Cm versus alpha was a zero slope, for any change in alpha throughout this graph, your Cm remains constant. Cm is constant. Cm alpha equal to 0 means Cm is constant. So no matter how much this changes, so it changes from 2 degree to 4 degree. So delta alpha is 2 degree. It changed by this much, but there is no restoring moment. There is no moment that attempts to bring it back to 2 degrees. So the aircraft continues to fly at this alpha equal to 4. So it flies at the 4 degree angle of attack. It remains over there. So it is neutrally stable. What is neutrally stable? Neutrally stable is when it moves to the new point and remains there. It has no tendency to come back to the original equilibrium point. Ready. Is it clear now, Jay? Is the neutrally stable part clear? When the aircraft has no restoring moment, it has no tendency to go back to its equilibrium point and it remains there. Hence, if the Cm alpha slope is 0, it remains at the neutrally stable point as the new location. So it's neutrally stable. Okay. Let's go on. Now we'll discuss a few questions from assignment 1 and assignment 2. Have you all attempted the assignment 1, assignment 2? Have you submitted all of them?
Yes, ma'am.
Okay. So positively cambered airfoil produces what? Considering leading edge moment is positive. We have discussed this in the first tutorial, I think. So can someone tell me what the answer would be? Positively cambered airfoil produces what kind of pitching moment? Someone? You've all submitted the assignment, right? So what answer have you given? 2. Negative pitching moment about aerodynamic center. So why? Let's just discuss that. So this is your cambered airfoil. Cambered airfoil center of pressure is here. And your aerodynamic center is the quarter chord point. So C by 4. And that is here. Now, all of your forces are presumed to act at the center of pressure, but we need to do the analysis at the aerodynamic center. Transferring these aerodynamic forces, lift and drag, to the aerodynamic center comes with a moment. Now, this lift produces pitch down moment, nose down moment at the aerodynamic center. So here you would have nose down. So the pitching moment produced at the aerodynamic center will be negative. So negative CMAC. That is the option 2. That's right. For a symmetric airfoil, where would the center of pressure be? What would the relation between center of pressure and aerodynamic center? Would it be ahead or before, or what would it be? Center of pressure and aerodynamic center. What is the relation for a symmetric airfoil?
Both are coincide.
Both are the same point. So it would have no CMAC for a symmetric airfoil would be 0. Okay, it will not change with angle of attack. It will remain 0. A wing made of symmetric airfoil, the pitching moment coefficient at 0 degree angle of attack will be, we just discussed this. What is this answer? Symmetric airfoil, pitching moment at angle of aerodynamic center. What would it be?
0.
0. Yes, we just discussed this because center of pressure and aerodynamic center are at the same point. It would produce no moment when we transfer the forces to the aerodynamic center. So the correct answer is 0. Right? Next, aspect ratio of an airfoil is. What is the formula for aspect ratio?
B square by S, span square is B.
So aspect ratio is B square by S. So for an airfoil, what is the span? B is what?
Infinite.
So this answer would be infinite. For a wing, for a wing is a finite length. So span for a wing is what? B square by S. This B is finite. So what would the aspect ratio be?
Finite and non-zero.
Will it ever be 0?
No, because not in any case span is 0.
Okay, correct. The aspect ratio of a wing increases. What is the relation between aspect ratio and lift curve slope? So the lift curve slope is, okay, so this is your lift curve slope. Say this is for aspect ratio 10. How would it be for aspect ratio 15? As the aspect ratio increases, the lift curve slope will
Decreases.
Are you sure? Are you sure it decreases?
Not sure.
Okay, it will increase. Okay, so this would be aspect ratio 15, and the highest one would be for aspect ratio infinity. So that would be for airfoil, and so on and so forth for other wings of finite span. Okay. Yes. To make a flying wing maneuverable, which of the following requirement must be met? Center of gravity should be. What is the requirement to make a aircraft stable? What relation between center of gravity and aerodynamic center?
Aerodynamic center should be behind center of.
CG. Correct. So for stability, you should have CG and then AC. Right? Now, maneuverability is the opposite. It's the opposite concept of stability. So more stable an aircraft, the less maneuverable it is. Okay, so for making an aircraft maneuverable, what should be the condition? Maneuverable means less stability.
Center of gravity should be behind aerodynamic center.
Correct. So this is for maneuverability. Okay, this is for stability and this is for maneuverability. You can also see it from this equation here. So the parts that contribute towards stability is this. Having this negative would contribute towards stability. For that, your AC should be after the CG. Having it positive would contribute towards maneuverability. That is done when the CG is, when this quantity is greater than this quantity, correct? Is it clear?
Yes, ma'am.
Okay. Next question, to trim a flying wing at negative angle of attack, which of the following arrangement is done? Similar to the previous question. What do we
Center of It would be ahead of aerodynamic center.
Think again, to trim it at positive angle of attack. So Cm alpha, we require positive Cm naught. To do this, positive Cm naught, what contributes towards positive Cm naught?
Airfoil should be cambered.
So the equation, where was the equation? This is the equation, right? This is the term that we need to deal with to make sure Cm naught is positive. This is Cm naught, right? So to make this term positive, trimming a wing at negative angle, make a flying wing negative angle of attack, this is the term that we deal with, right? So for a negative angle of attack, Cm naught should be
Positive.
for negative angle of attack. Cm alpha.
Negative.
An aircraft at positive angle of attack, we need to have Cm naught positive, right? To trim it at negative angle of attack, this is for positive alpha. For negative alpha, you need Cm naught to be
Negative.
negative. To have Cm naught negative, that is this term, for it to be negative, what do? You cannot deal with this because this term directly contributes towards your stability. It's the same term. So you cannot mess around with these terms, correct? You don't want to change the stability. So you can only mess around with this term. So what do you change in CMAC wing to make sure that Cm naught is negative? How do you get CMAC negative? For what kind of airfoils do you have negative CMAC? We just discussed, I think the second question was this. For symmetric airfoil, the Cm is 0.
Cambered.
Cambered airfoil, you have CMAC as negative. So this is the option. To trim an aircraft at negative angle of attack, that is to have negative Cm naught, you need to have a cambered airfoil. Okay?
Ma'am, can you please repeat how Cm naught is negative for negative angle of attack?
Okay. So this graph you understood? To trim the aircraft at positive angle. Where do you trim the aircraft at positive angle of attack? This graph, right?
Yes, ma'am.
Right? So for trim the aircraft at negative angle of attack, you would have a negative Cm naught. This is for positive angle of attack. Okay?
Yes, ma'am. Got it.
Now, longitudinal stability of an aircraft depends on tail arm, control surface area, types of winglet used in wingtip, or none of these. What contributes towards longitudinal stability? You remember those two equations from wing and tail contribution. Longitudinal stability, these two terms are the ones that deal with longitudinal stability. Of the given options, what deals with longitudinal stability? Tail arm, correct. So tail arm is this, it comes in this VH. So VH has the tail arm terminal. So it's ST, LT by S and C. This LT is the tail arm. Okay, so VH is equal to this and LT is the tail arm. So that contributes towards longitudinal stability. Next, negative tail incidence angle setting as compared to zero tail incidence angle setting will result in the negative tail incidence, that is IT. The positive or negative tail incidence angle, will it affect the stability? How will it affect the stability?
More static stability for negative.
Okay, anybody else? For a negative tail incidence angle, what would the stability be? Anybody? Okay, so I think we'll go back to that equation. This is the tail contribution towards stability. Is everybody clear with this equation?
Yes,
ma'am. Okay, so out of these two terms, this term and this term, out of these two terms, which term contributes towards stability? This is Cm naught of tail and this is Cm alpha of tail. Which term contributes towards stability out of these two terms?
First one.
This term to, so for static stability, our condition for static stability was Cm alpha should be negative. Cm naught should be positive is only to trim the aircraft at positive alpha, right? It doesn't contribute towards stability. The only term that contributes towards stability is Cm alpha. So for a tail, the only term that contributes towards stability is the Cm alpha tail. Is that clear?
Yes, ma'am.
Yes. So in this term, do you see tail incidence angle, does it appear anywhere? In the Cm alpha tail, does it appear anywhere? Cm alpha tail. What are the terms here? So VH is tail, horizontal tail volume ratio. Eta is the efficiency factor. Cl alpha tail is the lift curve slope of the tail. This is the downwash component, and this is the alpha of the wing. So here, where is the tail setting angle in this equation? Which term represents tail setting angle? Can someone tell me which term represents tail setting angle? IT, exactly. IT appears in Cm naught, right? Cm naught has no contribution towards static stability. So this IT, changing IT does not change Cm alpha in any way. So changing IT has no effect on the static stability. So a negative tail setting angle, positive tail setting angle, it would have the same static stability. Is this clear? Is this clear? Is everyone clear with this?
Yes, ma'am.
Okay. So the tail setting angle has no effect on longitudinal static stability. Okay. In an aircraft, without changing any other dimensions, the area of the horizontal tail is increased by 3 times. Due to this, the longitudinal stability of the aircraft will. Now, previous question, they asked you the effect of tail setting angle on stability. Here, they've asked you the effect of tail, horizontal tail area on static stability. What would the answer be? What would the answer be? What is the effect of horizontal tail area on static stability? Let's go back to that equation. This is the tail contribution towards stability. This part, everyone is clear? This is Cm naught again. And this is Cm alpha of tail. Okay. Now, this is the term that contributes towards stability. And where does the horizontal tail area appear in this equation?
In VH equation.
In VH. So there is VH here. It contributes towards stability, right? So VH is tail area, tail arm by wing area and wing chord. Okay. So if you increase the tail area, does the static stability increase or decrease?
Increase.
Increase. Correct. Is everyone clear with that? Did everyone understand why it's increase? Is everyone clear with that?
Yes, ma'am.
Yes. Anyone else has any questions with this? So I'm guessing not. Moving on to the next assignment. This is assignment 1, assignment 2. Which placement of wings gives more longitudinal stability of aircraft? So I had given you a clue in the last class to do the analysis, like this would be the CG. For a high wing, your aerodynamic center for high wing would be here, and aerodynamic center for low wing would be here. So now you take the aerodynamic forces acting about those two. Now, which one would give you more longitudinal stability? Low wing, yes. Can you tell me why low wing is more stable? Devansh, can you tell me why did you say low wing? Low wing is more stable. It contributes towards stability. Why? Or can anyone else attempt why it would be more stable? I've drawn the forces here. So if you can tell me how it contributes, how it produces moment above CG. CG. Because it will give nose down moment when disturbed. Okay, so how we do this is, this lift component for high wing, let's do for high wing. This lift component would produce a nose up moment at CG. That component would also produce a nose up moment at CG. Okay, is that clear? For a high wing. Yeah. For a low wing, the lift component while producing pitch up, drag component will produce pitch down. So compared to a high wing, low wing produces some negative component of moment, right? So this drag term would give you this kind of a moment at CG, right? Pitch down. So for a low wing, the drag term produces a pitch down moment. So hence low wing produces is more stable than a high wing configuration. Okay, clear? Just let me know if you have any questions at any point.
No, ma'am, clear.
Which type propeller configuration gives less longitudinal stability? Doing the same analysis as before, can someone tell me? So pusher and tractor. Pusher is when the propeller is after the CG. This is pusher and this is the tractor, okay? Okay. So now when subject to an angle of attack, this thrust, so propellers produce thrust, there is a component of thrust in this direction, which produces a moment at CG, right? This is pitch up moment. Now pusher produces pitch down moment. So which one would be less stable?
Tractor.
Huh? Tractor would be less stable, right? This produces a pitch up moment, correct?
Yes, ma'am.
Okay. Now, in an aircraft, the size of elevator is decreased, keeping the vertical tail volume ratio constant. How will this affect the longitudinal stability of an aircraft? It's similar to one of the questions in assignment 1. So vertical tail volume ratio is constant, but elevator size is increased. Elevator is the control surface on the tail. That size is increased, keeping the vertical tail volume ratio constant. How will it change the stability? Can someone attempt?
Remains same.
Remains same. Why? Again, we go back to this equation. This is the term that contributes towards stability. Now they are saying that VH again same is ST LT by SC. Now they're saying that this VH is remaining constant, but elevator size is changing. What does that mean? This ST remains same. Even if the elevator size is increased, the overall tail area remains same. So it will not have any change on the stability. So size of elevator does not affect the stability. Okay. Next. For a conventional aircraft, the sign of Cm alpha and Cmq are respectively what? Cmq we have not dealt with till now in the lectures, but you should be able to do the same analysis as Cm alpha. Now, what I said in the previous slides was when subject to a positive angle of attack, change from the equilibrium. So initial airfoil, this was equilibrium, and this is when subject to a disturbance. You need to have a negative pitch moment, which is why Cm alpha is negative, right? What is Cmq? Cm alpha is what? Cm alpha is dCm by d alpha. Cmq is dCm by dq, and q is the pitch rate. Okay, we have not come to this term yet, but pitch rate. So the rate at which the aircraft pitches is q. Okay. So is Cmq clear? Yes, answer is both are negative. Cmq is just like Cm alpha. So why is Cm alpha negative? Why do we need Cm alpha negative? So for a positive change in alpha, you need a restoring moment Cm. Okay, so you need a negative Cm. For a positive change of alpha, you need a negative Cm. For a positive pitch rate, you need a negative Cm. So both of them have to be negative. Both the slopes have to be negative. Okay. Yes, clear?
Yes, ma'am.
We have not dealt with Cmq as of now, but it was fairly simple. Okay. With the increase in horizontal tail volume ratio of the airplane, the elevator required for a given CL trim will be. With these equations, can you say? With the increase in horizontal tail volume ratio, the elevator required for a given CL trim will be. Okay, let's just do this. So suppose your initial CM delta E was minus 10. Okay, I'm just taking some random values. These are not the typical values at all. So delta E trim for first case would be, suppose say CM naught was 5. Okay, so just take 10. Okay, and your CM delta E was minus 10 plus this was some value 5, say, and CM delta E was minus 10 and CL trim 1. Now for the next case, it says that the with the increase in horizontal tail volume ratio, that means the CM delta E2 would be, suppose say, minus 20. Okay, delta E trim 2 would be, this will remain same, minus 10 by minus 20. The CM naught part will remain same, correct? It's 10. Plus again, this XNP minus XCG remains same. Tail volume ratio has no effect on XNP position or XCG position. This would become minus 20 CL trim. CL trim is same. Okay. So now tell me if this value would be more or this value would be more. Take CL trim to be any value. Take CL trim to be 1. What is this value?
First value is more.
First will be?
Will be more.
Minus, how much is this value?
Sorry, first value is less and second is more.
Correct. Second value is more. So the final answer is more. Correct? Do you agree with me? Delta E2 is greater than delta E1, right?
Yes, ma'am.
So the answer is more. Okay. The static longitudinal stability of an airplane is provided by what? Simple question. Again, take the equation for CM and tell me, was it vertical tail volume ratio, horizontal tail volume ratio, both of them or none of these? What contributes towards static longitudinal stability?
Horizontal tail volume ratio.
Yes, this VH, horizontal tail volume ratio. VH. Two aircrafts are geometrically similar, but the first one is bigger in size and mass compared to the second one. Which one will be more stable? This was another question that was asked in the forum. What have you guys written for this? Similar, geometrically similar aircrafts, but what, the first one is larger in mass and size. Okay. So a larger aircraft, that is a heavier aircraft, by virtue of its inertia, tends to be more stable to any external disturbances, right? So it's harder to disturb a heavier aircraft. Do you agree with me? It's hard. Yeah. So the heavier aircraft would be more stable, right? Agreed. So that is the answer to that question. I'm not sure who asked this in the forum, but a heavier aircraft is more stable as it is harder to disturb the aircraft. Okay. The position of a neutral point of aircraft is 0.5 meters from the leading edge of the wing. The location of center of gravity of the aircraft is 0.4 meters from the wing leading edge. What is the location of the aerodynamic center of the aircraft from wing leading edge? This, I think someone had asked in the previous tutorial and I said I will discuss this. Can someone tell me what the right answer would be? They've given you neutral point, center of gravity. They've asked you to find the aerodynamic center of the aircraft. All are measured from the wing leading edge. So what they've given you is, so CG is here and neutral point is here. Okay, so they've asked you where the aerodynamic center of the aircraft is. Where would it be? Someone? No? So I told you at the beginning of, beginning of the first lecture, this neutral point is analogous to the aerodynamic center. So aerodynamic center for an aircraft is equal to neutral point. Aerodynamic center of an aircraft is nothing but the neutral point of the aircraft. So the answer would be 0.5. Neutral point is 0.5 meters from leading edge. Aerodynamic center will also be 0.5 from leading edge. Okay?
Yes, ma'am. For each and every aircraft, aerodynamic center is equals to neutral point.
Yeah, if they say aerodynamic center of aircraft, that is the neutral point of the aircraft. There is one question in your third assignment. I wanted to discuss this. I think it is the 8th question, 7th or 8th question, I'm not sure. They've asked you to find the distance between neutral point and aerodynamic center. So it was the 7th. So assignment 3, question 8. They've asked you to find the distance between neutral point and aerodynamic center of aircraft. So that is a mistake there. You need to find the distance between neutral point and aerodynamic center of the wing. Okay. So this is what is given, but this is the correct one. Okay. Just
Yeah.
okay. It's clear?
Yes, ma'am.
Okay. Question number 8 of assignment 3. Okay. So aerodynamic center of an aircraft is the neutral point. Next. Which one is correct about a stable aircraft? Again, this question should not have been there. Maneuvering point we have not discussed. So we'll discuss this question when that topic comes up, okay? In-flight measurement of neutral point. At neutral point, which of these values hold true? So we know our graph, DCL, D delta E. This was delta E and this was CL. Trim. Right. So I said that as we move our CG towards the neutral point, CG1 is the CG to this neutral point. As we move the CG towards the neutral point, that slope becomes 0. So at neutral point, slope is 0. So this would be the correct answer. D delta E by DCL trim at neutral point has 0 slope. Is 0, correct? Yeah?
Yes, ma'am.
Okay, so you understood this question, right? Why it would be 0?
Yes, ma'am.
To solve your assignment 3, we had discussed this question in the last class. I'm just going to briefly go over the slides from last class just so that you will be able to solve the question in the assignment 3. The data given in the question is the weight of the aircraft at cruise, cruise velocity, the surface area of the wing, the cruise altitude density, the aspect ratio of the wing, the CG location, aerodynamic center location, moments and lift at the aerodynamic center, the tail setting angle, wing setting angle, zero lift alpha, and the efficiency factors, vertical, horizontal tail volume ratio, tau, delta E max. Okay. Using these values, first they've asked you to find the lift coefficient for cruise. At cruise, lift equal to weight. So you can take weight as the lift component and find out the lift coefficient. We did this in the last class. I'm just going to go over this to help you solve the assignment 3 questions. Okay, so this is the equation that you follow to calculate CL for cruise. This lift is equal to weight. The other terms are given there. So you get CL. Next, they asked you to calculate the downwash angle, that is epsilon naught. We know the formula for epsilon naught. You have this, okay? And they've given you the slope of the lift curve slope is given. CL versus alpha, lift curve slope is given. They've given you at zero lift, what is the angle of attack. So you can find CL naught just by taking the slope and multiplying this absolute value, right? So CL alpha is this one, zero lift angle of attack is -2. Multiply those two to get CL naught. Put this value here, you get epsilon naught. We discussed this in the last class, which is why I'm rushing over this, okay? So you get epsilon naught. Then they've asked you to find out Cm naught of the aircraft, assuming the fuselage contribution towards Cm naught is 0. So the Cm naught contributions would come from wing and tail. We know the formulas for Cm naught of wing and tail. This is given in the first slide. All these values you have substituted, find out the two Cm naught wing, Cm naught tail, add both of them to get the entire Cm naught contribution. Okay?
Yes, ma'am.
Okay. Next, they've asked you to find the Cm delta E, the slope of the Cm versus delta E. Okay, again, you know the formula for that, again, given the couple of first slides. You know each of these values, calculate Cm delta E. Then they've asked you to find static margin. Static margin is the difference between neutral point and center of gravity. Neutral point and center of gravity both are given in the equation, in the data for the question. So the difference between these two, you get static margin. Now using all these values, they've asked you to calculate delta E to trim the aircraft. So they've asked you, what is the delta E trim to trim it at CL trim. Here in this case, trim would be cruise. So you've calculated the CL for cruise. Use that CL. So CL cruise is equal to CL trim, right? So use that CL value to find out delta E trim from this equation, right? This was clear in the last class, right? I'm just going over this. Is this question clear to everyone?
Yes, ma'am.
Okay. Next question is find the elevator control power in radian. What is elevator control power? What is the term that represents elevator control power?
Delta E.
What? I didn't hear you.
CM delta E.
Exactly. CM delta E is the elevator control power. How do you calculate CM delta E from these values?
CM delta is nothing but dCm by d delta E. So here
Correct.
both dCm will be.
Right. So here it would be 0.08 minus 0.02 by minus 2.5 minus 1.1. What is the value? What's the value? Can somebody just calculate and let me know? Okay, let me calculate. 0.08 minus 0.02 divided by minus 2.5 minus 1.1. So it's minus D. Okay. Right? Is that value? Does everyone agree with that? D? Okay, so it's D. Now, if we have to calculate, this is the slope of this. Right. This is the slope, correct? CM delta is the slope. Can you calculate the intercept now? Will you be able to do that? I think the questions in the assignment, one of them says, how do you calculate the intercept? So you have the slope and you have 2 points. Can you calculate the intercept? I'm not going to do this, but the equation for straight line is what? Y is equal to mx plus c. M we have slope, Cm delta E. So M is equal to Cm delta E. We have M, you have the points Y and X. You take any point. Can you calculate C? Yes? Just plug in these values. Cm, just take in any Cm1 is equal to Cm delta E and delta E1 plus C. This will give you the intercept. I think one of the questions in the next assignment asks you to find this intercept. Okay, I'm not going to do this. Is this clear? Okay, we'll discuss the assignment anyway after the due date is over. That's the next class. So does anyone have any questions in this entire tutorial or anything in this last 3 weeks? Any questions? This question is clear to all of you, right?
Yes, ma'am.
Okay. Initially, they asked you to find out CL for cruise, which is CL trim. Then they asked you to find the downwash angle. Then CM naught, that contribution of the tail and the wing, you do that. CM delta E, values are given directly to you. Find it. And static margin, again, neutral point CG given to you. Use all of these equations in delta E trim equation to find out the delta E. That's all. Anyone has any questions in anything that we discussed in this entire class or anything for the past 3 weeks? Any questions? No? Okay. So next class, we'll discuss the assignment 3. The due date is tomorrow, right?
Yes, ma'am.
Okay. So all the best for that. We'll discuss the assignment in the next class. If there are no further questions, I think we'll end the class here. Okay.
Thank you, ma'am.
Thank you. Thank you, everyone.
Thank you.
Thank you. Okay, I'll just send you the link for the YouTube videos. You have the link, right? These are the links for the YouTube videos where these lectures are uploaded. So I'll end the class here. Thank you.